It's the James Webb Space Telescope. So I hope you can see my screen, right? It's up there. Okay. So I even title this talk the exploring distant exoplanet atmospheres with the James Webb Space Telescope, and we're gonna kind of embark into this adventure of figuring out what the Webb telescope is doing for us, trying to explore these worlds out there. So before we go into the whole science thing, I think it's very, very, very important that we settle ourselves on where we are, because this is a very human quest, right? We're talking about worlds farther away than our own, than the usual ones that we're used here in the solar system. And I think it's very nice to settle ourselves into the space of human. So basically, if you start to think about every book that you've ever read, or all the life forms that you can think of, even of every relationship that you've had in your life, all of that it's a lot. It's for us humans. All of this is like a lot of information. All of that lives in this very tiny blue dot, as the late Carl Sagan used to call it, called Earth, right? And this appears to us as like a very, very big environment. As you mentioned, you were just mentioning before, like there's a lot to learn even from this very, very small planet. But this is just one out of the 8 or 9, for those of you fans of Pluto, planets out there. And that actually makes us look kind of tiny. So this is like a selfie that was taken from the Cassini-Huygens mission. There was basically when this was in Saturn, it took a selfie. And I don't know if you identify yourselves in this photo. If some of you probably have seen it. You are here. You're this little dot that you're seeing here behind the fantastic rings of Saturn, right? And if that doesn't make you feel a little bit tiny, then look at this picture, right? This is, of course, we have not managed to see to take a selfie from outside of our galaxy, but this is our best understanding of how our galaxy structure is. And we are just one little dot in this picture, like our sun. If you imagine to bring this to scale, if your screen, when you're watching this, was made to scale, like the sun would be like a little molecule, right? So it's very, very small. We're like very, very tiny in the grand scheme of things. And if that still doesn't make you feel small, that you're one part of these 100 billion stars in our Milky Way galaxy, we are just one out of the hundreds of billions of galaxies out there, right? Again, we don't have the technology to go out and take a selfie from a faraway galaxy, but this is a very beautiful picture from the James Webb Space Telescope, one of the very first like deep fields, like just James Webb stared like at a blank region of the sky, and they saw this, right? So it's really, really fantastic that to think that we're just this little point out there, out of these many, many galaxies. So let's do the math kind of together. So if you think about this is 100 billion stars per galaxy. That is the average number of stars per galaxies. You multiply that by 100 billion galaxies in the universe, and I'll let you do the math. That's a lot, right? It's full of possibilities out there, and this is the very exciting part of studying exoplanet science. In that we have very, very exciting statistics about worlds about there. Like imagine the possibilities. Imagine if this is the number of stars out there, and we're just one out of those. Imagine all the possibilities of worlds out there that we can imagine. It really goes beyond your imagination, and science has this thing of being better than any science fiction picture that you can get of. But the statistics that we know is something as follows. So if you go out there tonight, like after this talk, hopefully, well, it's very cloudy and now, but when it's not cloudy and you go and look at the sky, just point at a random star. We know that on average, every star has at least one planet. So you point at a random star, chances are that you're also pointing at a planet orbiting that star. And we call those exoplanets. And it's full of worlds out there. We're big worlds, small worlds like our own, giant planets abound as well. So it's really a crazy universe out there, playing with possibilities of what these worlds might be. Now, the reality is that while we know that there's one planet around every star, we have not discovered all of them yet. And there's many, many missions trying to uncover them one by one. To date, the number that we have, this number was reached like a few months ago. we know in the order of like 6,000 exoplanets outside our solar system, planets orbiting other stars. This is a very big number that has grown tremendously from 1995 when the first sun the exoplanet orbiting a sun-like star was discovered. That the number was in the single digits by 1995, and now kind of 20 a little bit above 20 years later, we are at the 6,000 mark. As I'm going to tell you at the very end, this number is going to explode in the next few years. So if you're really interested in exoplanet science, now today is kind of the best era to be alive hearing about this stuff, because it's getting really, really exciting. The method by which we discover planets, actually, it's a very smart method. What we do to discover the vast majority of exoplanets is that we just look at each star out there. And sometimes when planet passes in front of the stars, as you see in on this graphic in the bottom left, sometimes when that happens, the planet kind of blocks part of the starlight and leaves like this decreasing flux as a function of time. And if you observe that periodically, you basically have a planet. Of course, there's a lot of work behind when you're trying to make these measurements, but that's how we discovered the vast majority of exoplanets. Now, if you think about this method is actually a pretty lucky method. Like, you have to be inclined such that this planet actually passes in front of you and you can see this effect. And that inclination, again, you have to be quite lucky to do that. But as humans, we're very smart, and we've figured out ways of monitoring the brightness of like millions of stars at a time, and that's how we get like these very very nice discoveries. In particular, the Kepler mission was one of the kind of pioneers and champions of discovering the vast majority of exoplanets that we know of today. If you now this is the picture of measuring these transit events, right? But measuring these transit events is very, very, very hard. Like the classic approach that we do to this is that the easiest planets to discover are the ones that are bigger, because the bigger your planet, the more light they block in your star, right? And if you're trying to detect like an Earth-like planet around a sun-like star, it's a very tiny decreasing flux. This is like being in Maryland and trying to measure like a light bulb all the other way from California, from like a little fly passing in front of the light bulb. So that is like a very, very tiny amount. And this is the kind of signals that we're looking for. So doing this actually is pretty hard. So if you try to measure these precise transit events, say from the ground, for instance, this is the kind of data that you get, the red points in here. And you see it's very hard. It's not like the textbook light curve that I show you, that decreasing flux. This thing is much more ratty, and that's because of the atmosphere, right? So the flux from the star that it's coming through the atmosphere really moves around, and that creates all these sort of things. So now we've gotten pretty smart on trying to figure that out, but still, it's very, very hard to deal with that. You might tell me, Nestor, but now we have space telescopes. Yes, here's an example from from the Hubble Space Telescope in the middle, and from the late Spitzer telescope on the right. And they also show it's not easy even from space, right? There's like all the little wiggles that you're seeing that get away from these little trends. It's all related to the detectors and the stability of the observatories. So to measure this kind of events, you really need like very, very, very stable instruments, very stable observatories that can really monitor this brightness like with this extreme precision that we need. And the story that I'm going to tell you is that basically this was hard until the James Webb Space Telescope. What I'm going to show you next is, I think, a very, very exciting moment in my career, in the career of many other folks that were in commissioning in James Webb, to check during commissioning, to check that James Webb was working as we expected. We took a transit event, and I had the privilege of reducing and analyzing that data when it came when it came down. And look at these light curves, and this is the kind of light curve that we measure like right off the bat from James Webb, right? It's like very beautiful textbook kind of transit event as the planet is passing in front. I always tell this story that when I was reducing this data, at the very first, when I reduced this data and I got this beautiful light curve, I thought that I was reading my simulations. I had a lot of simulations, like with perfect stability, and I thought this was the simulation. So I triple checked, and this is like the real data. It was pretty exciting to know that James Webb was going to do this kind of science with exquisite precision. You can also see in the x-axis the time at which all of this happened in Baltimore, Maryland time. And this was very, very early in the morning that I had to wake up to reduce this data. So it was very, very exciting morning. I do have, of course, to introduce a little bit the James Webb Space Telescope. I already told you it's awesome. But I want to tell you also that it's an engineering marvel. And I always like to introduce this as like the craziest space idea ever, because as I'm going to tell you, it's such a crazy engineering experiment, really, that I would have loved to be in that board meeting that decided this thing, to hear someone propose this and everyone going like, this is crazy. Like, how are you going to do this? Um, so the James Webb Space Telescope, you're going to see it here unfold, was so big, first of all, that it had to unfold in space, basically, almost alone, right? We had no one trying to do all of this that you're seeing here. All that you're seeing here, the unfolding of James Webb, happened in the course of like a month. And it was truly a marvel to see this thing working as it happened. So this is a 6.5 meter diameter telescope. The whole structure is like the size of a tennis court. So it's very big, a lot of complicated things going on and all of this. It's at like 1.5 million meters, kilometer distance. This is like 5 times the distance from the Earth to the Moon. So it's very far away in a point called the L2 point. And the last point I think is the key one, is it had over 300 single points of failure in the unfolding that you just saw. I'm just gonna go back so you can see it again. All of this that is happening here involves over 300 single points of failure. That means that there were over 300 mechanisms that you're seeing here, that if one of them fail, that's it, mission over, right? But again, when we humans get together and use their intelligence for like innovative things and innovative solutions, we manage to do stuff like this, which is completely crazy. So that's why I like to tell that Webb is like this crazy space idea. Um, so if we take a look a little bit at what kind of exoplanets the James Webb Space Telescope is looking at, I want to compare them to what the planets in the solar system that you're seeing here as little pictures. And what I'm going to do is that I'm going to plot them. I think this is the most complicated plot that I'm going to show. So in the x-axis, I'm showing the orbital distance in astronomical units. So 1 astronomical unit is like the distance from the sun to the Earth that you're seeing here at 1 in the x-axis, the bottom axis. And in the y-axis, you're seeing the planet mass in Earth masses. So 1 is the Earth, around 300 is like Jupiter, and around 100 is Saturn. So these are the planets in the solar system. What you're seeing right now are all these 6,000 exoplanets that I told you about. And the next points that you're going to see are the exoplanets that James Webb is looking at. And you can see that it's exploring really all the parameter space of the exoplanets that we know of. Not all of them, not the 6,000, but in the order of like 200 to 300 exoplanets so far. We have James Webb for many, many more years, and many more will get explored, but these are the ones that we know of. If you want to know why the colors, I can explain that later, but the important bit is that every colored point here is an exoplanet that James Webb is looking at. And I really want to focus in this talk on this region that I find extremely exciting. Is these are worlds that are more or less the mass of the Earth, for which we are exploring what the composition of those planets is. And I find that fascinating. It almost sounds like science fiction, but James Webb lets us get to the point in which, kind of science meets these science fiction stories of trying to figure out the composition of worlds out there. The big question that I have to pose before jumping into that is why, right? Why are we interested in figuring out the composition of worlds out there? Well, this is a kind of a portrait, a family portrait of all the rocky planets in the solar system. Mercury, Venus, Earth, and Mars. And if, for an astronomer perspective, the size of these planets is more or less the same. Like it's like 1 Earth radii, give or take, right? So if you only know the radii, which is what you know by the transit events, you only get the radius basically in terms of what you can measure. You can measure also the mass, but at the end of the day, we don't get, just by measuring one transit event when it's discovered, we don't get to know what the composition of these worlds is. But as you can see by the colors here, you already see that they have different compositions in their atmospheres at the very least. And I'm not a very judgmental person in general, but when it comes to vacation destinations, which is something that I like to do from time to time, I'm very judgmental. And what I want to show you is my own ranking of like the terrestrial planets, the solar system as vacation destinations. And it's to make the point of, how special is this beautiful world we live in, right? So let me kickstart this with a ranking of 5 stars, and I'm giving 0 stars to Mercury as a vacation destination. Now, don't ever go to Mercury. It's like it's awful. If you go, it doesn't have an atmosphere, so you can't breathe, you die. And even if you manage to not die, you go, and if you're in the day side, you can cook a pizza basically of how hot it is. But then in the night side, if you go to the night side, then you can freeze that pizza. So it's really not a very great vacation destination at all. Next one in my list is Venus. Venus, it's also an awful planet to be in, and as good humans, we love too little atmosphere or too much atmosphere. Venus is a world that has way too much atmosphere, so much that if you decide to bring your car to the surface of Venus, it will get crushed because the atmospheric pressure is so high that you'll have so much atmosphere on top of you that the cars just get crashed. It's worse, you cannot park, right? And it's too hot because of this atmosphere. Too cloudy, you can't see anything. So, pretty awful place to go on vacation. Mars is great I give it 1 star. And the reason I give it 1 star is because it has robots. And we all love robots. We've sent them there. The population of Mars is dominated by robots right now. Problem is that it has little atmosphere, so you will also very likely die if you go unarmed, and unequipped, basically. So guess who gets 5 star out of 5? Is the Earth, right? As someone mentioned in the comment, the Earth is an excellent place to go on vacation. Has a nice atmosphere. Most of your friends live there, and it has Wi-Fi, right? And it's great. You can get connected with everyone. So the reason why we can build this ranking for vacation destinations is because we know what their atmospheres look like. So their atmospheres are a key parameter for us humans to understand how habitable, say, a world is, and even to understand and map what it looks like, right? This is exactly why I'm so excited about the composition and measuring the atmospheres of exoplanets. So when a planet transits its star, we have this beautiful opportunity to measure the atmosphere of the planet, because part of the starlight goes through the exoplanet atmosphere when the transit is happening. And if we put like a little prism of that light, we can figure out what light the atmosphere is actually eating up from the planet, to try to figure out what the composition is. So this is like a very fantastic technique that was predicted back in the early 2000s by Sarah Seeger in particular, that was championing this from MIT, that is now moving to Toronto. And this is before I hope I convinced you that the transit event is like a very tiny thing. Measuring the atmospheres through these transit events, it's an even tinier signal. And in the early 2000s, when this technique was being proposed, it's called transmission spectroscopy. People told Sarah Seegan and other people out there that this is like you can't measure this, like there's no way. And as I'm going to show you in a bit, we use this routinely right now, 25, 26 years later, to characterize the atmospheres of worlds out there. So what we do basically is that if you have a gas like an atmosphere and you filter some light through it, this atmosphere, depending on the composition, it has its own barcode. Like every molecule we know has its own diet. Like water, for instance, love to eat infrared light. Sodium loves to eat optical light, and so on. So this is a spectrum actually that you're seeing here. It's a spectrum from the sun. And every little barcode that you're seeing here is one gas molecule in the atmosphere of the sun, right? And you can actually pick out what kind of composition the sun has out of just pictures like this, trying to figure out we call it the spectrum of the sun, and trying to figure out what light is missing. You can get the barcode and compare that barcode to the barcodes that we know from Earth, from laboratory experiments, on what it is composed of. I also think that that's like a very fantastic thing of astronomy, the fact that we can combine lab measurements on how we know molecules eat light versus what we observe from exoplanets very, very far away, right? The fact that we can just think about this stuff, I think we should be very proud of the kind of stuff that we can think of as humans when we get together, like kind of for good, so to speak, in our curiosity to understand the world. So yeah, each line is an atom or molecule kind of eating light, which is exactly what we do to measure what the composition of planets out there is. And again, this is not science fiction anymore. We can do it for exoplanets. As I'm going to show you, we are trying to do this even for terrestrial worlds, like small planets orbiting distant stars. Now, I did tell you before that we have this statistic, right, that out there, if you point to a random star, a lot of there's a lot of planets out there, on average, one planet per star. The other thing that I haven't mentioned yet is that the average star out there is very alien to what you're used to every morning. You wake up in the morning, you look at the sun, and it's this like orangey star in your sky, or yellow, or that looks up and it's very big and so on. But the reality is that out there, if you point to you pick like a random star from our galaxy, the random star is actually very tiny. So the average star in our galaxy is very small and very red. So here's a comparison of what like an average star in in the galaxy looks like, and it's like very tiny. It's like 1/10 of the sun. It's very very small. It's very cold. The sun, as you're seeing here, has in the order of like 5,700 kelvins, but then the small stars have like kind of half of that temperature. And we actually know that if the average planet basically lives around this kind of star too. This also provides an opportunity for us to explore what we call the habitable zones of these stars. These habitable zone, there's people that hate this concept, there's other people that love this concept, but the habitable zone of a star is this zone, this region around the star in which you're not too close, such that water will just evaporate because you're too hot in your planet, and also you're not too far away and cold, such that that water will freeze. You're right in the right spot in which, if you had an atmosphere and if you have liquid water in your surface, you would have it. You have it in liquid form. For sun-like stars, that's pretty far away. It's this 1 AU distance, which is like hundreds of millions of kilometers out of the sun. But for cooler stars, because they're cooler, just like a heater, if you want to feel the same heat, you have to get closer if your heater is smaller. And the habitable zones of these stars is actually closer to their stars too. And this is beautiful because it's, first of all, they're easier to detect. If you have a planet in the habitable zone of a red star, the year, how long it takes to go around, it's in the order of like a week or a few weeks, depending on the size of your star. So you can, if you transform the habitable zone from the sun, and we like magically convert the sun to like a reddish star, like this average star out there, and we put the Earth around some of those stars, we would celebrate New Year's like every week, which would be fantastic, many parties and everything. But also it makes it very nice for characterizing this atmosphere. You don't have to wait a year to watch these transit events. You only wait a week. And that's like timescales that are very, very small to do this kind of measurement. Now, this is a double-edged sword, however. Being closer to your star is great from a perspective of detecting it, but it's also pretty dangerous in terms of the activity of the star. In the last few days, we've seen from our sun, for instance, this level magnitude events of flares and activity that the sun produces because of its magnetic field. And these small stars are also very crazy. They also produce like a lot of flares and a lot of activity. And being closer to your star raises also the possibility of one of those flares just blasting your atmosphere. So it's a double-edged sword in the sense that we don't know if rocky planets around these small stars, they actually get to survive these kind of events. And this is a very, very big question. Like, do rocky exoplanets around these small stars actually survive and are able to retain their atmospheres? It's a big, big question that it goes in line with what I'm going to present in a little bit. There's one particular little star that I'm really, really obsessed with. And this is what I wanted to introduce next. It's a very, very cool planetary system that it's called the TRAPPIST-1 system. If you've not heard about it before, you're in for a treat. It's a very, very cool system. So the TRAPPIST-1 star, first of all, is as alien as it gets. The star is as small as Jupiter. You heard that correctly. The star is like the size of Jupiter. It's like the size of a planet in our solar system. So it's very, very small. It's very, very cool. It's around 40 light years away. So if we send like a light signal there, it will take 40 years, which is in astronomical terms pretty nearby. And it doesn't have 1, 2, 3, or 4 rocky planets orbiting the star. It has 7, at least 7 rocky planets orbiting its star. And this is the cover of the magazine in which this system was introduced. And I really love it because it's like a really nice mesh between science and art. Because the table shows you the habitable zone, right? So you see the closer planets have this vapor going around. And the reason that they have this vapor going around is that they're so close that if they had atmospheres like the Earth, water would evaporate because it's just too hot. But the planets that are very far away, you see ice in the table, right? And that's because it's too cold, right? The water will freeze. But if you look closely, the planets in the middle, there's water, and they are in the habitable zone. There's like 3 or 4 planets, depending on your definition of the habitable zone, that are in that zone, which is pretty exciting. So that's one of the part of the alien parts of this system that I'm really fascinated about. There's another part that has fascinated a lot of people. And of course, sorry, before we go into that, these planets have names which are boring. They have codes depending on which ones they were detected first, and not like TRAPPIST-1b, C, D, E, F, G, H in distance from the star. And of course, I'm also trying to build this vacation destination ranking for these ones. And we already know that the closest one, TRAPPIST-1b, is an awful place to be because by James Webb observations, that I'm not going to show today, but I can show them later if you want, we do know that that planet doesn't have an atmosphere. The atmosphere is like very thin. So if you go unequipped, again, you don't have an atmosphere to breathe. But all the other planets, the jury's still out. So they could have sizable atmospheres, and who knows, maybe life could emerge in some of these planets. The other very alien thing that I find fascinating about this system is that it's a very compact system. It's so compact that if I could just like snap my fingers and bring it to the solar system, which I'm doing in the bottom part of the picture here, the 7 rocky planets will fit very snugly within the orbit of Mercury. So they're all very next to each other, which is crazy. It's so crazy that the orbits of the planets themselves perturb the other orbits. So they don't go around their stars like little clocks, like in their solar system. The new year, so to speak, shuffles around for a couple hours, or sometimes many hours. So if you wanted to celebrate New Year's, you will have a hard trouble figuring out exactly when to pop your champagne bottle because the thing just shifts by hours every year. And we can see this from the data. But the other very exciting part of that is that the planets are so close together that if you looked in the sky of one of those planets, you could see the other planets in the sky, like basically moons in the sky. So what I'm going to show you next, it's an illustration. It's not, we haven't been able to travel to this thing yet. It's an illustration of what it would be to stand on TRAPPIST-1e, assuming that it has an atmosphere like the Earth, which we don't know yet, and I'm going to show you how we're trying to figure that out. This is an illustration of how that will look like. So you see how in the sky, again, because the system is so compact, you could see the planets in the sky like big moons, and you can even figure out, yeah, you know what the weather looks like in your neighboring planets. If you had friends, if you're trying TRAPPIST-1e and you had friends in TRAPPIST-1d or TRAPPIST-1g, you can call them and tell them, hey, there's a storm coming up, because I can see it, right? Which is it's very exciting for many reasons, but also from like a human perspective and imagination as well. Now, of course, as I was telling you, we're trying to build this like vacation destination ranking, and I've been particularly obsessed with this one, TRAPPIST-1e, which is kind of in the middle of this habitable zone. There's many reasons why it's very special. First of all, its year is like 6 days, so every week you get a transit of this planet. That means that there's many opportunities to observe it with James Webb. And we have a couple programs observing it in detail to try to figure out what the atmosphere of TRAPPIST-1e looks like. And that's the story that I'm going to explain you next. This is the first exploration of this, went in a couple of papers late last year. So this is like very fresh out of the press. And I'm going to tell you a bit about like a follow-up program to that as well. So I haven't told you, I have hinted you how we do this exoplanet atmospheric exploration, but in particular, what we do in practice is that we try to measure these transit events at different colors of light. This is what you're seeing here. And at the colors of light in which you have like an observer, the planet looks very big. So what we do is like we measure basically the size of the planet or the size of the transit event as a function of different colors of light. And then whenever you have a big radius, like given wavelength at a given color of light, then that means that you have an observer and you might have a molecule in that color of light. That's what we're trying to hunt with this kind of observation. So measuring these transits at different colors of light. And this is exactly what James Webb is able to do very precisely. So what I have here is one of these plots of this, what we call transmission spectra. The x-axis I have colors of light, The more to the right we go, the more redder the light that we're measuring is. And in the y-axis, what I'm going to plot is the transit depth, like the how deep that transit is as a function of the colors of light. So we were trying to basically try to discern three different models, which are plotted here in different colors. The purple model is assuming that the atmosphere of this TRAPPIST-1e planet is filled with hydrogen. So when planets form at the very initial stages, the disk, when they're accreting material, is filled with hydrogen. That's the majority of the gas in every disk that you see when planets form. And it is believed that some planets might absorb a lot of this hydrogen and maintain it for a sizable amount of their lives. So this shows like one of those hypotheses. What if this planet holds to that hydrogen atmosphere? And you see that the features, like the bumps and wiggles here, are huge. And the reason why they're huge is that because hydrogen is very light, and therefore it uses a lot of space. And then the transit signature that they produce when they pass in front of the stars is huge, right? So that's why you're seeing these very, very big features here. The blue model that you're seeing here is what if TRAPPIST-1e was like an Earth-like atmosphere? So if you pass the atmosphere of the Earth and you just put it magically in TRAPPIST-1e, this is what it would look like in this kind of plots. And I'm going to explain what these wiggles are in a minute. But what I want you to focus on is that the signatures are very, very small. And the reason for that is that our atmosphere, that the one that you're breathing right now, is basically filled with nitrogen, and nitrogen is much heavier. And because it's much heavier, then the atmosphere is much, much snugly coupled to the planet. It's much smaller. And that means that the signatures too on these transit spectra are much smaller. There's, of course, the third possibility that I was explaining before, in which what if it has no atmosphere? And if it doesn't have atmosphere, then as a function of the colors of light, you will measure the exact same transit event, like it's exact same transit depth, because it doesn't have an atmosphere, so there's no wiggles, because there's no different elements absorbing if it doesn't have an atmosphere. Now, this was observed back in 2015 with Hubble. And Hubble has a very narrow wavelength range. So you can only observe like a certain amount of colors. It's very precise though. Like the fact that Hubble could actually measure this transit event is huge. But really with Hubble, we were not able to tell apart the Earth-like atmosphere with the hydrogen-dominated atmospheres. It was really hard for us to conclude anything with this data. So what I'm going to show you next is what we got with James Webb. And with James Webb, you have many, many advantages. First, the precision is beautiful. It's like the error bars are like very small, but also they cover a wide wavelength range, like run from like around 0.6 microns, which is like the light that you can see right now. It's in the order of like the left-hand side, all the way to the near infrared to all the way to 5 microns. That's the beauty of James Webb. It can really get you all the colors of light with extreme precision. And now we're in business, right? Now we can really rule out that this planet that this planet had a hydrogen-dominated atmosphere with the Webb data. And I'm going to do a little close-up into this because the error bars get so small that you really need to do that close-up. So I'm going to do a little close-up here. And there's many things that I want to take out from this plot. So first of all, in the y-axis, I'm plotting this in units that might be a bit alien to you, which they're called parts per million. And this is like the brightness change is on that we're trying to measure from different colors of light. It's in the order of like 50 parts per million. So if you have like a million photons, you're trying to look for 50 that kind of wiggled, which is it's very, very crazy. To translate this to, I'm sure you're all very good readers, to translate you to like finding typos on books. This is like finding 50 typos in all of Shakespeare's plays. So if you go and you put all the Shakespeare's plays in the room and you find 50 typos, that is the kind of precision that we're looking with James Webb at each of these colors of light. That is insane. It's very, very, like the fact that we humans are able to even get to this, it's fantastic. And all of these wiggles that I'm showing you here, they represent different molecules too. And that's the other exciting part. So we can see, if we got even better precision, we could see methane, CH4, water, H2O features, CO2, above 4 microns, and even CO, and even there's some marks of ozone here and there all around. But sadly, with this first data that we got, which were 4 of these transit events, around 20 hours of JWST time, we were not able to discern between the Earth-like and the no atmosphere. Basically, these data points pass through the blue and the yellow models, right? So I'm not able to tell you, yeah, this is like an Earth-like, or yeah, this is no atmosphere right now. Luckily, we got very excited about this and by the precision that we could get with just 20 hours of telescope time. So we asked for more telescope time. Now, asking for telescope time with James Webb, it's a whole endeavor, right? You have to write big proposals. You have to gather teams with all the expertise. So this was a whole adventure on its own. And we asked for a very sizable amount of James Webb time. You're typically lucky to get like, 10, 20 hours of JWST time. Like that's like, wow, you shout and then you create like a little party within your group, right? Here we were asking for like 5 times that time to really nail this down. So it was a very ambitious program. But the good news is that we got it. So we proposed and we got the order of like over 130 hours to study TRAPPIST-1E through a GWS2 program with a grad student in my group, Natalie Allen, that is now graduating, with honors by producing a proposal together in our group as PIs, co-PIs with Natalie on this program, which is fantastic, right? And in your grad school, you can actually propose for big projects for a very ambitious programs, like trying to discover an atmosphere now around a habitable zone planet out there. It's fantastic. So keep an eye out for this. We have like 95% of the data right now with us that we're analyzing from now until the summer. And hopefully maybe next year we can chat again and I can give you an update on what the atmosphere of TRAPPIST-1E is. Now, what about other systems? So I've told you one system I'm obsessed with, but there's other planets out there too. And the big question to try to explore other rocky worlds out there is how do you pick the targets? And there's like an idea going behind that, do you remember that the question that we had was like, which planets retain their atmospheres? And there's 2 sides of that coin. So first of all, smaller planets, like the ones in the left here, have weaker gravity, and therefore any molecules can escape very easily to space. But if you have a planet like the one in the right that is larger, more massive, then it has more gravity and it can really hold to its atmosphere, right? So bigger planets will hold easier to their atmospheres. And on the other side also, depending on what kind of star you have, if you have more radiation coming from your star, then these molecules will have more energy and they will dissipate. But if your star is like very quiet and doesn't give you too much radiation, then the molecules won't have the energy necessary to escape. So you have kind of this 2-sided coin. It's like how good your planet retains to the atmosphere, but also how your star is behaving. So there's like these 2 axes. So in the x-axis here, I'm plotting like how hard it is for the atmosphere to escape the exoplanet, the planet's gravity, and then the y-axis is how much radiation you get in the planet, with up being more radiation on the planet. Basically, you want to be in the bottom right? You want to be in that zone in which your planet really holds to its atmosphere and you have low amount of radiation. Because if you're in the other corner in the upper left, then you have a star that is really bombarding with radiation, and your planet is too small to hold to the atmosphere, like in the worst case, in the worst part. This is the concept that some people have built here in the solar system called the cosmic shoreline. The sign that even in our solar system, if you look at the planets in the bottom left here, Mercury, Venus, Earth, Mars, and the Moon, the objects that have atmospheres like Venus, Earth, and Mars, they are indeed in that bottom right corner. And objects that don't, like Mercury and the Moon, that are in the kind of top left part of the sky. So we have actually identified a set of exoplanets that are kind of the best to explore in terms of observability, in terms of how long their years are, and how well James Webb can observe them, which are the ones in open circles here, to explore whether they have atmospheres or not. And we are embarking into a big program right now called the Rocky Worlds Director's Discretionary Time Program. This is actually a joint program between James Webb and the Hubble Space Telescope. And here's where I wanted to make the Hubble Space Telescope also shine. Rocky Worlds is one of these directors' initiatives, the director of the Space Telescope, that is analogous to, probably you've heard of the Hubble Deep Field Image. The Hubble Deep Field Image was one of these directors' discretionary programs that the director of the Space Telescope decided to just point to like a blank point in the sky and just observe what kind of galaxies we obtain from that. I was like, these crazy ideas that required a large investment of time that the director of Space Telescope had. Rocky Worlds is one of those initiatives. the director of Space Telescope asked the exoplanet community what kind of program we should build. And this was the result of that community input on what kind of programs should go on, what kind of targets should we observe. So these are, you remember that I told you that we were very happy to win like 100 hours of JWST time? Well, this Rocky World's Director's Discretionary Program is 500 hours of JWST, like 5 times that time, right? So it's a large investment of time. And it's also 250 HST orbits. And the reasoning for that is that what we're doing right now is that James Webb is really looking at their atmospheres, trying to figure out if they have atmospheres or not. But the Hubble Space Telescope is looking at the stars. It's trying to figure out how the UV radiation from the star, what kind of radiation the UV radiation from the star is emitting, because that is key to understand why they might or might not have atmospheres. The UV radiation is key to understand the escape of these atmospheres from these planets. And this is really where the Hubble Space Telescope shines. It is the only space-based observatory that really can do UV astronomy with this precision. This is kind of like the dream team of astronomy, like, James Webb and HST kind of like logging in and locking in into a common project, which is fantastic. We have a webpage that you can visit. The whole point of the Rocky Worlds DDT program is that the observations are publicly available. We reduce the data and we put it out for the community to do science with it. So it's like a very community-led program that we're really, really, really proud of. And in particular, I'm pretty proud to be leading this at Space Telescope with a fantastic team of astronomers trying to put all these products out there, including the visualizations that you're seeing here. The technique that we're using, actually, also I wanted to introduce it because it's different to the technique that I mentioned of transmission spectroscopy. Transmission spectroscopy, when the planet passes in front, right, in this figure here, but the planets also pass behind, and they play this hide and seek. And that's actually a very fantastic technique to measure what the day side flux, what is the actual flux of the planet. You can actually measure the flux from the day side of the planet. And that actually lets you measure kind of the temperature of the planet. It's a way of measuring, it's like putting a thermometer basically on the day side and saying how hot or how cold the day side is. Depending on the composition of the atmosphere, the temperature is going to be different. So for a given amount of radiation on an object, the atmosphere, if you have an atmosphere, that atmosphere is going to redistribute that energy all around. This is like in our cold, in this current cold Maryland winter. This is like having a heater in just one part of your house, and then if you had it outside, if you open, you remove your roof. If you put a heater in one side of your house, it won't heat up the house. The heat will escape, right? But that's why you put insulation into your house, because that heater then with the proper insulation maintains the heat all over your house. This is exactly what the atmosphere does on the Earth. On the Earth, the day side receives the sunlight, but then that is redistributed because we have this roof, which is our atmosphere, that protects that heat from going outside and heats the entire thing. And therefore, the same amount of energy is redistributed all around, so the planets look cooler. So that's what you're seeing here as a thermometer. Like the Earth looks very, very cold in comparison, for instance, with Mercury or the Moon itself. If you go and measure the Moon, the day side of the Moon is very hot. The night side of the Moon is very cold, and that's because it doesn't have an atmosphere. You remember I told you that Mercury is very hot in the day side, like as hot as like to cook a pizza, but in the night side it's cold enough to freeze it. That's because it doesn't have an atmosphere, right? It's the no roof case in this heater exercise that we were just doing. So we're trying to do exactly this measurement with all these exoplanets with this Rocky Worlds DDT program, it's really exciting. It's just starting, so people are gearing up in excitement of this. And again, HST is measuring not only the UV flux, but also trying to measure if there's sometimes flares. We can measure them in the UV, which is absolutely fantastic. So yeah, please take a look, and if you have more questions on Rocky Worlds, happy to. Now, I've been talking a lot about like rocky exoplanets around these small stars, but you might be wondering, well, Nestor, what about planets like ours, like our planets, or like planets around sun-like stars? And they exist out there. We know through, like, statistically there should be others out there, like Earth 2.0, so to speak. And the statistic basically what goes as follows. For sun-like stars, the statistic right now is like every 2 sun-like stars, one might host a planet like the Earth. Like that's the statistics that we have. If you randomly pick 2 sun-like stars in the sky, on average, one has to have like an Earth-like planet. more or less. The tricky part, though, is that this is all statistics. This is all extrapolation from what we've seen. We don't have a single twin system that we have identified as of yet, like an Earth-sized planet at an Earth-like distance around a sun-like star. That might change, however, with the Nancy Grace Roman Space Telescope that it's up to launch not earlier than this year. It might launch this year, but no later than next year. And that's going to find in the order of like 100,000 new exoplanets. You remember at the very beginning, I told you that right now we know 6,000 exoplanets. Well, when Roman launches, if you wait 5 years until the main mission completes, we're going to have in the order of like 100,000. That's going to be a huge explosion of worlds. And Nancy Grace Roman might actually uncover these Earth-like planets around sun-like stars out there, which is very, very, very exciting. The next frontier is that I've talked to you about spectroscopy and doing this through transits, but there's new observatories that we're thinking of in the 2030s and 2040s, like the Habitable Worlds Observatory. And I cannot give a talk about exoplanets without talking about the Habitable Worlds Observatory, because it is the first time in the history of astronomy in which a flagship mission, like Hubble, like Webb, that we're planning an observatory for exoplanet science. All the other observatories, and including James Webb, have been made thinking on cosmology, on big questions about the galaxy and the galaxies and the universe around us. But it has never been dedicated to put the specs on the observatory to measure exoplanet science. And the Habitable Worlds Observatory is going to be the exception. And that's why, of course, as an exoplanet scientist, I'm really, really excited about this. And the dream with this observatory is not to get you these spectra only, it's also to get you pictures. This is an actual simulation of what like an observatory like the Habitable Worlds could do, which would imply trying to take with a very smart technique, like a little picture of like the Earth, like the solar system, for instance, in this case, that you could see like a little point orbiting around kind of the star in the center. And the way this is done, it's actually pretty smart. It's another technique, in which you use a coronagraph. The problem with observing and taking pictures of planets is not that they're faint. In fact, we're able to detect galaxies that are at the very beginning of the universe, like very far away. So the faintness is not the problem. The problem is the contrast. The problem is that just when you're at night trying to check what kind of car is coming at night, it's just too bright. The stars in the center are too bright, but we've figured out ways of like blocking that starlight. And now you can observe the exoplanets around. This is basically what you do with these techniques, like trying to suppress the starlight from the center. Now, to do this, you need technology to suppress that starlight to 1 part in 10 billion. That is so insane that I'm pretty sure that no one can really put a number into that. So I brought you an order of magnitude statistic on this. In case you love the Ravens, or even if you don't, if you have like a random football stadium, this is analogous to trying to stabilize every single hair on every person in like a Ravens full stadium game. You try to stabilize every hair. That's what 1 part in 10 billion looks like. It's completely crazy. But we humans are very smart folks, and I think we can figure that out quite nicely. And there's experiments that show that we could get there. So that's the kind of, from space, right? So maybe stabilizing the hairs of people here seems more doable because you tell everyone to like lock their hairs. But in space, that is like, it's very, very hard to do. But we're thinking of some way of doing it. And not only that, of course, if you take the picture, it will look like a little pixel. But the idea is to get spectra of this, just as I showed you before, but this is direct spectra, which will be fantastic because when you're trying to think about measuring the spectrum of Earth-like worlds out there, you also have to think about time. And this is what these plots show. In the y-axis, you have like the age of the Earth, and you can see how the atmosphere of the Earth has changed. This is what each of these plots shows. At the top, you have the Archean Earth and how the Earth was at the very beginning when it was forming. And the middle, you have the Proterozoic Earth, like once it evolved into like some initial life, and the modern Earth spectrum in the bottom, and they all look very different. So when thinking about spectroscopy and trying to measure molecules in other worlds, you have to think as a function of time, because Earth has looked like very different if you take pictures of the spectra of Earth as a function of time. And that's very likely to happen with worlds out there, and the Habitable Worlds Observatory will be able to measure that, which is a dream come true. All right, So with that, I would like to kind of end and open for questions. So let me give you a little summary. So the James Webb Space Telescope is exploring atmospheres of a variety of exoplanets, including those inhabitable zones of red dwarf stars, which is very exciting. The Hubble Space Telescope is exploring these UV environments, key to understand the evolution of their possible atmospheres, and we're even using them in tandem to understand rocky worlds out there, like the Rocky Worlds programs that I introduced to you. Thinking on the future, we have the Nancy Grace Roman Space Telescope, which will uncover in the order of 100,000 new exoplanets, 20 times what we know today. And the Habitable Worlds Observatory aims to obtain the first images and spectra of Earth twins around sun-like stars. It's a very bright time to be alive, very bright time to be studying exoplanets. So thank you for giving me the opportunity to share the excitement with you folks, and I'll be happy to take questions.
Thank you so much. This was a great presentation. If you can stop share, come back, I'll stick a spotlight on you, and we can open it up for Q&A. We do have one question right now in the chat box. You can put your questions in the chat box, or you can raise your hand, and I would be happy to call on you. Robert is asking, how will the Nancy Grace Roman NGR find so many more exoplanets than the James Webb? Will it orbit an L.2?
That's an excellent question. Yes, it's going to go to L2, but the reasoning behind why it can detect planets is the following. So the James Webb Space Telescope, really the vast majority of the work that it's doing for exoplanet science is to characterize the atmospheres of other worlds, which are like through spectroscopy, like I just showed. That is the majority of what the work of James Webb is doing. So it's characterizing the atmospheres of already known worlds. It's not really a discovery machine, but there's some projects that are actually using it to discover new planets, but it's a small fraction of what the telescope time is used for. And the reasoning for that is that James Webb really has like typically holds like a very small field of view. So if you point it to the sky, the regions of the sky that it observes is kind of small. It's like focused on a set of objects instead of like a big object. That's the beauty of the Roman Space Telescope. The Roman Space Telescope is designed as a survey telescope. And the idea is that it can observe very large regions of the sky. The footprint of Roman in the sky is very big. So if you kind of map how big the observatory can take a look at in the sky with all its detectors, it can observe like at a time a region as big as the moon in the sky. And that's huge for a telescope. Like it's a very big region of the sky. Therefore, it lets you monitor many millions of stars at a time. And that's exactly where it wins. It wins in the numbers. It wins in the numbers of stars that it can monitor at a given time. So it's designed to do these kind of searches.
Well, Mark has a whole bunch of questions about the James Webb, and I can refer him also to the past presentations that we've had and all about the ins and outs of it. But how do you reposition? Like if you need to, who controls it, and how do they reposition the James Webb to go where you want it to go?
Yeah, that's something we're very proud of the Institute. So they have the mission operations and control at Space Telescope. So a lot of that kind of sending commands to the telescope so that it can observe. All of that it's done in Baltimore itself in the Space Telescope Science Institute. So that is another part of the challenges that we do in the Institute that I love. It's like a really nice connection between like mission operations, mission engineering, spacecraft engineering, trying to define, okay, what's going to get observed next week and the week following. And so planning the schedule, like the planning, we have a team called the Planning and Scheduling team at Space Telescope that kind of thinks about all of that and repositioning, making sure that all the systems are in place and so on. So there's a team of people that work on this at Space Telescope that whenever I get the chance to speak with them, I'm always impressed on the kind of expertise that has to merge to make that happen. You can already, by the words that I'm trying to use here, you can understand it's a very complicated process, but we have a lot of talented people at Space Telescope doing all of that it's a pleasure to be able to work with them. Yeah.
So we have Clark was saying, extending your statistics, there should be billions of Earth-like planets in green zones.
That is correct. Yes. To be very honest with that statistic, so I said that the average is every two sun-like stars, one Earth-like planet. But to be honest, that has a very large error bar right now. And that is why one of the reasons why I'm so excited about the missions that are upcoming. Not only the ones that I mentioned, there's other missions like the Europeans, for instance, in leading the Plateau mission that is going to uncover more, hopefully on Earth, an actual Earth twin out there. The Chinese are also building the Earth 2.0 missions, like another telescope to do like a survey of trying to detect these Earth-like worlds. So as I mentioned, all these statistics are extrapolations from what we saw from Kepler in particular. But we don't have, again, one example of like a true Earth twin around a sun-like star right now. I cannot point you where that is right now. But I think these upcoming missions could uncover that. And that would really settle that number to a very precise number. So yes, in theory, the average should be in the billions. There's a big error bar in those billions as well.
Preston has asked, how come different planets are different sizes?
Well, the reason why I'm in Europe right now is because there's a workshop they invited a few of world experts to try to figure out questions like that, especially for small stars, for planets orbiting small stars. I mean, the reasoning behind planets in different sizes has to do with how the planets form. When the planets are forming initially, if you, it's all a race to try to form like a very big core. If you form a very big core, if you manage to grab like a lot of rocks when the planets are forming, if you form a rock that is like in the order of like 5 to 10 times the mass of the Earth, then you very quickly start accreting a lot of gas from around you. We call it runaway gas accretion, and you form a giant planet. So if you get to that mark of like 5 to 10 Earth masses, then you form a giant planet. But if you don't, if you fail to form that amount of mass, then you get to stay tiny like us, like our piece of rock, like a failed giant planet, right? It didn't make it to that big masses. Um, so it couldn't accrete all this hydrogen. And all the atmosphere that you're breathing right now didn't really come from absorbing from that initial disk. Most of the atmosphere that you're breathing right now comes from outgassing. Like eventually all of this gas was trapped in rocks. Eventually it got hot enough that all of those rocks started outgassing these atmospheres, and this is what you're breathing right now. So the sizes depend on how you manage to accrete material when you were forming, and then the composition of the atmospheres depend a lot on whether you were big enough or small enough to accrete or to outgas your atmosphere. So, but exactly the distribution of sizes that we see as a function of like the orbital periods, for instance, it's still a big question. And then in the workshop that I was, we were discussing this exactly. Like, why do we observe the distributions that we observe? And many people are really scratching their heads trying to figure out exactly, trying to understand the population of worlds that we see. And that is the other beauty of the missions that I was talking to you about, that it will bring larger sample sizes, and that will solidify these statistics much better in order for the theorists to figure out, okay, no, it's this particular process, or and so this is efficient, and so on. So it's a big question, actually. Yeah.
So I have a question. When you put in the last part about the different signals that the different atmospheres of Earth made over time, you know, the early Earth, middle Earth, and now current Earth. So if someone were out there taking pictures of us right now, would they be which atmosphere would they be thinking we are? Would they possibly be thinking and seeing that we are the archaic Earth?
There you go. Sorry, I was the button was not working. That's a very good question, and I think you're referring to the fact that uh, you know, aliens looking at or from or within our galaxy looking at us will be looking kind of in the past a little bit because light takes some time to get there. Now, the distances in the galaxy in terms of the timescales of evolution of the atmosphere of the Earth, the lengths of distance on our galaxy are much smaller. So the diameter of the galaxy is in the order of like 100 million light years, which means that if you're from one side of the galaxy to the other, it takes like 100 million years for the light to get there. Now that seems huge, but if you transform that to like a time scale, in the numbers that I was giving you, those where we were talking about 4 billion years. So that is much smaller than this distance. So an alien located in the other side of the galaxy, it was basically observing the atmosphere as we were observing it, like, 100,000 years ago, which is not that much different to what we're seeing right now. They wouldn't see the impact of technology, of course. So that's the interesting bit, I think, that technology is a very recent thing, like in the last 100 years. So only the stars that are within 100 light years from us are able to detect any signs of technology from our atmosphere. All the rest of the stars, light has not have enough time for that information to get there. So that's another of the interesting facts too. When you ask, like, are we alone in the universe? You have to think not only about time, but also about distance. So for every star that is trying to observe our planet at a distances larger than 100 years, they do not know that we have technology on Earth, right? Because light has not reached them yet. So communication, it's a big issue.
Cool. Mark asks, do all planets around different stars align on the same plane like our solar system?
That's a very good question. The vast majority do. However, the key part of that question that I loved was asking our solar system. So if you plot like the how thin that disk is, it's very thin in the solar system, but it still has like thickness. There's like a degree of inclination that is kind of random on which planets are located. It's very small. It's like a few degrees, but that few degrees are important, and it depends. That tells you the story a little bit of how the solar system formed. And there are planets out there in which we call them mutual inclinations. We call them are much different than the solar system, and that's because they might have had a formation that was much more chaotic than what we experience here in the solar system. So there are people, and this was part of the questions that we were discussing too in this workshop here at Lund, trying to understand that mutual inclinations from different systems, and it's a fascinating subject on its own. So the answer is like, mostly, yes, but not exactly like the solar system inclinations and distribution in the disk.
Robert wants to know if the detecting a light bulb in Baltimore from California is a good mathematical estimate, or was it just an illustration? And what's the trick to such fine light detection?
Yeah, I think the order of magnitude is more or less correct. But the way you can derive this has to do with the angular visual of how far away it has to be like almost a point source. And I think the tricky part is there is like figuring out the light source versus like the mosquito or fly going in front. But I mean, if you have more questions about that, I can give you the exact order of magnitude and how you arrive at that. But it's more or less correct, I think. Yeah.
All right, any more questions tonight or early morning for Dr. Espinoza over there? Working out, how many astronomers worldwide are using James Webb?
That's a good question. I cannot remember the number from the top of my head. What I can tell you is that I can tell you the number of people that want to use the telescope, first of all, as an order of magnitude. In the last cycle, so every year we have an open call for proposals. So people write these big documents to try to make their case to get some telescope time. Last year, deadline was in October, and we got almost 3,000 proposals. Now, on average, every proposal has to have in the order of like 10 people on average per proposal. So if you multiply that, it's like in the order of like tens of thousands or more probably that want to use the telescope. Now, a small fraction of them actually get the time, like 10% or less. So it's in the order of like maybe thousands of people. But now that's divided into groups. Like the number of proposals that actually get it are in the order of like no more than 100 proposals get the actual time. So like 100 programs per cycle, and that's 210 people. So I guess that is the order. Like around 100 teams get telescope time every year, on average. But that I did all of that in the spot. If you want the more concrete, correct numbers, there's a very and maybe we can put it in the chat later, and I can share the link later. There's reports that Space Telescope generates with these kind of numbers, trying to figure out, how much, where the telescope time is going, geographically, and also the numbers of people that are getting the time.
So with the time, does money come with that, or you have to find your own money?
That is an excellent question. So typically, for depending on where you are in the world, it comes with money. So for US-based astronomers, we do get funding associated with this. It's a two-step process. You get the time first, and then they ask you to build a budget to actually, develop the program and analyze the data and publish that data. That's how we hire, grad students, postdocs, and so on. But then different countries around the world do it differently, and the timescales for doing that too is different. But in general, James Webb comes with money, but then where that money comes from, for US-based astronomers, that comes from NASA, but from other institutions around the world, they come from their own governmental facilities and associations. Yeah.
Clark asks, has any planetary disks been imaged outside of our solar system?
Yeah, that's an excellent question. Yes, and actually, James Webb is very good at imaging disks, and in particular, disks composed of like the reminders of planets once they are formed. So yes, there's many images. The most beautiful ones that I've seen, of course, come from ALMA, the Atacama Large Millimeter Array in the Atacama Desert in Chile. Those antennas are fantastic for imaging these disks of like uh, kind of planets caught in the act of forming, basically, which is amazing. But yes, James Webb also has done this, and it's its own field as well.
So, anybody else out there? How does the data turn into photographs?
Oh, that's an excellent question. I don't know if this is open. So there's a whole team at Space Telescope that they're experts in doing this, and that's a fascinating subject on its own, which is like a different talk at all. Um, because when you read the data of these images, you read numbers. You read how many counts did you get in a particular pixel, and then you take those images with different filters, and then you have to combine them somehow. Um, and when deciding how to combine, you have many philosophies on how you should do that. Of course, all the light that the majority of the light that James Webb observes is light that we cannot see. So you cannot translate that directly to your eyes because our eyes are just not made for that, which is a beautiful concept on its own. Like the fact that we as humans can actually build instruments to be like another pair of eyes different to us is just fascinating. So then I think the strategy that these folks use, however, is how do you maximize the information content in these images from the different colors? And these are the images that you see. So they are fake in the sense that they're trying to maximize all the information coming from the different colors, but also they are real in the sense that you're observing this through a different lens, through a different pair of eyes, which are James Webb, and that gets translated to you. So whenever people say like, oh, I remember my wife one time told me, but these are fake photos, as I explain it. But I was like, but you can think this as like a super brain that is actually making better photos that our eyes can look at. And I find that fascinating. Like the fact that our human eyes they're great. We get pretty, we look around us and the world is beautiful, but you can make kind of the world beautiful with the right instrumentation and the right brains. And that's what the people at Space Telescope do in the Office of Public Outreach, which are fantastic. I mean, that way of combining those images is just genius. So yeah.
Let's see. Noah has, what kinds of atmospheric mixes would you expect to see on rocky planets? Are there any of them easier to spot than a nitrogen-dominated atmosphere like ours?
That's an excellent question, and the answer is yes. The easier ones to spot would be carbon dioxide dominated atmospheres. And the reason is that in the plot that I was showing for TRAPPIST-1e, the biggest feature that you could see was carbon dioxide. So if you have a carbon dioxide feature, that is the one that will pop up first. And the more you have, the bigger that feature is. So yes, the easier ones to detect out there are carbon dioxide dominated ones, which is pretty exciting because Mars and Venus are carbon dioxide dominated atmospheres. So we're we would be very sensitive to atmospheres like that, like the ones we see in the solar system, which is very, very cool. And in terms of what would we expect, that I'm very agnostic about. Because in the solar system we see naturally dominated, carbon dioxide dominated. Um, but then depending which group you ask around the world, some of them will tell you like, well, oxygen dominated atmospheres as far as we know, also very possible out there. So we really we're going in the blind here on what we should expect. So again, I'm really agnostic to what we should expect from these atmospheres around these rocky worlds, around M stars in particular, and these small red stars.
Yeah, keep an open mind, because then you don't have some bias built into what you're seeing in your data. So also, Mark might have some money or wants to get some money to do a grant. How much money is it per grant that these
That's
projects
a
cost?
very good question because until the last cycle, this was a very complicated process that it was hard to tell how much money you were going to get. Right now, it's much more, let's say, normalized that the more hours your program asks for, the more money you will get because the program gets more and more complicated with more hours. On average, I would say like each grant is like a 60,000 grant, which is like enough for like a grad student for a year. It's not like a lot. You don't get like millionaire, and you don't hire like a lot of people in one grant. But is sufficient, of course, to reduce and analyze the data. If you have other team members as well, and you can redistribute the load in two teams. So that's why you don't go into James Webb proposals kind of alone. I don't think anyone can do it alone on this. You need like teams and to distribute the load of work across many team members all around the world, and that's kind of the expectation too, right? So that's
I
the order of
think
magnitude.
Yeah, I think that's too little. We should be putting much more resources into this work and discovery than other places that it goes. But that's just my opinion.
Well,
If
I
I
agree.
if I were writing the checks, I'd put a couple more zeros behind that for y'all to keep doing what you're doing, because it's pretty amazing out there, and I love your passion, enthusiasm. The information has been wonderful tonight, and I do believe that we've all fallen in love with the TRAPPIST-1e. So you were correct today.
I'm glad that I share the excitement for Travis Bunny.
Yes, we all have that. Um, so thank you so much for staying up with us, and thank you so much for all of the work that you're doing. We hope that you'll come back and keep us updated as you discover new things with your 500 or 750 new hours that are coming online for you. Congratulations on that.
Thank you.
And for everybody, thanks for joining us. Hope to see you next week, where we're going to be back on Earth looking at the farmland raptor preservation program. Then caterpillars and trees. So every Tuesday, it's something else on Must Learn Tuesday. So thank you. Stay well, stay curious, stay warm out there. Cold blast is coming our way again. Take care, everybody. Good night.
Thank you. Bye bye.